Well,
You guys with me on that?
yeah.
Now, a couple things about this. If we look at this picture, this is your unbalanced force here, but that would be the same size as this, as that there. You see how those two would be the same size?
Yeah.
They're the same part of a rectangle. Does that make sense?
Why is there two Afghans?
Because the road itself actually pushes you up and in, but we break them up into two conceptual differences. One, this is the road flat pushing up, straight up. We call that the normal, that's the perpendicular. And this is the frictional component that's providing the anti-sliding force that pushes you in. Both of those are provided by the road.
Okay.
So when we go to calculate the angle of lean, we say, well, how much did he have to lean? Now,
You said
no.
Yes.
I do too. Like,
This is
One of the things you'll notice here is that if this is your angle, the opposite side would be equal to the frictional force. The adjacent side would be equal to the normal force. And so you can write a tangent statement that relates these three things.
wait, F over F Fn.
Okay, you guys with me on this? All right, so if I go to calculate it, so the inward force was 395 newtons. The up and down force was 3,200. And I got about 7 degrees.
All right.
Anybody else get 7?
Yeah, I got that.
Oh, I did get.
Yeah, I
got
got
7, but I didn't know if to add a zero.
Sure.
So I messed it up.
I actually ended up, I got all threes on this one.
I should have gotten.
The next part is actually, you actually already get the second part, yeah?
How did you get the angle? Isn't it like the opposite
Thank
side
you.
over the adjacent?
So when I look at this angle right here, the side that's opposite is this one here, but these are the same length. So this would also be 395.
Oh.
You see how these would be the same length because they're, is that cool? And then this, if this isn't obvious to you, in order to solve for the angle, you have to do the inverse tangent of both sides. Is that something you guys know how to do?
Yeah.
Barely.
On a calculator.
That's fine.
I don't
Kind of
think
need
you
it on
get
that. I don't know if any of us should.
No. I mean, there are, sometimes you can do it, but
Just need it.
this is a 7-degree angle. We're not going anywhere. Okay. Now,
I could have sworn we had a unit with like a
if you remember, this is one of the things that we use to calculate.
Yeah.
All right. This says that if you want to calculate the frictional force, you need to know 2 things. What's this symbol represent?
Mu.
Coefficient of friction. What's this one?
Normal.
Normal force. Now,
Net force.
the thing says.
Hold on.
It's 50 times 10.
Like, don't you have to do more to get the 395? Or did I do one? No.
Well, he just kind of shortened it.
It's right here. You do mv squared over r.
Oh.
He didn't like write it out.
Yeah.
It's still.
I'm asking. Oh, no.
Yeah. So you had to calculate it using mv squared over r.
Yeah.
Yeah. But here's the nice thing about this. As long as you've structured your force diagram correctly, you actually know everything you need. What's the value of the normal force?
Did you not?
The normal force is 3,200 and the frictional force is 395. And so if you just solve for that.
Oh, so those numbers are supposed to be the same?
Yeah.
Bad.
Okay.
What would this be the answer? Oh, this one. It's number 10.
It's new, I don't like this.
Yeah, I know, but that's like the whole thing though, is this is the moment where you go from either not knowing to knowing, or like, oh, that's what that was? Oh, so annoying, right? But that's what I like. Like, you're supposed to be annoyed in this moment that you didn't get it right the first time. So that, like, the next time you're like, yeah, I do get this. All right. The next one,
What is it?
the next one I really like. So, one of the things that,
It's like what happened at this one.
Wait, which one was this?
Do you need a set?
this is the second last one.
Okay, I'm just double checking.
So, one of the things that we realize after we've drawn the force diagram is that the frictional force is the centripetal force. So you can calculate it just using mv squared over r straight up. Is that cool?
Yep.
So then this question says, if you doubled your speed, how much more friction would you need? So it says, if the speed is doubled, by what factor does the frictional force change?
How did you
Okay.
remember that?
What's that?
How did you remember that question?
I mean, I wrote it, I graded 100 of these, I had this class earlier today. You know, man. And it's my job. It's the JOB, man.
Alright, should we be done with the now?
Is it twice?
No.
I think for SAT.
Stay focused, please. When you look at this, what do you notice about the v in this equation?
It's square.
It's squared, which means if you increase your v by a factor of 2, it's going to quadruple because 2 squared is 4. What would happen, and get ready to check your neighbor on this one, if you tripled your speed, what would happen to the amount of frictional force needed? It would increase by a factor of what? Check your neighbor. Yeah.
It's 3 squared.
So it's not 2 cubed, it's 3 squared. Okay, so what would happen? If you tripled your speed, what would happen to the frictional force?
9.
Go up by a factor of 9 because this is squared in this equation. Okay?
Oh. Oh, it's the square of that.
It's the square, yeah.
So
Now,
quadruple.
and, moment of truth,
Because why?
because the equation is squared. So if you look on the right side here, so if you look on the right side, if you increase v by a factor of 2, 2's in parentheses, right? So in order to keep this equal, I would need 4 times the frictional force. Does that make sense? And if you made this increase by a factor of 3, 3 squared, you'd have 9 times the frictional force. All right, Lauren, read us the last question.
What force pushes the rider outward as he makes a turn? Just the higher answer.
All right, I know you guys aren't going to like me, but trick question, man. No outward forces.
Yeah, secret answer is C, story of my life.
No outward forces. I know you feel like you're being pushed outward, but that's just a feeling, man.
He missed it. There you go.
Does it justify it's just a feeling?
Yeah.
Yeah, so listen to this. Listen to this little description. It actually turns out that that feeling is something we feel all the time. So visualize this. You're at a red light, it turns green, you stomp on the gas pedal and you accelerate forward. What do you feel like?
You feel like you're being pushed back.
Okay, this is important. You feel like you're being pushed backward, but is there anything actually pushing you back?
So I'm gaslighting myself?
Well, kind of, but it's a real feeling. When your acceleration is forward, you feel like you're being pushed back. Now, when you brake, what do you feel?
Don't feel like you're going forward.
But the car is actually slowing down. There's nothing actually pushing it forward. So your acceleration is back, but the feeling is forward. So we have this sense that the way we feel about our motion is opposite the actual direction of acceleration. When you accelerate forward, you feel like you're being pushed back, and when you accelerate back, you feel like you're being pushed forward. when you're spinning in a circle, you feel like you're being pushed outward, but which way is your acceleration? It's in. So that feeling is actually, it has a name, it's called the centrifugal pseudoforce.
Alright.
What?
Whoa, that's like, yeah, never again.
It's called centrifugal
You don't need to
pseudoforce.
Centrifugal pseudo?
Pseudoforce,
Oh, so it's a fake force, because it's like
Yeah.
pseudoscience.
yes.
It's big.
It's an
Um,
imposter.
This is on. This is regular physics class.
all right,
Is there a regular?
yeah. Any questions before we stop?
Not Mr. Data.
No, yeah.